So the James Webb Telescope is the end of a series of infrared telescopes in space. It's much bigger than we've ever launched before into space. In fact, it's bigger and more sophisticated than any telescope, much less an infrared telescope.
Really what makes it special is that it's opening up a new wavelength regime, and so it's going to show us quite a new view of the infrared universe. One of our key goals is to find the first galaxies, so we'll be able to trace things a lot further back to the Big Bang than we have before. I'm Marcia Rieke, and I'm the team leader of one of the 4 instruments on the James Webb Space Telescope.
And I'm George Rieke, and I'm the co-lead on the second of the 4 instruments on James Webb.
T-6, 5, 4, 3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
In the 1980s, there was a program that NASA ran called the Great Observatories. And the Hubble Space Telescope was part of that program, as was the Spitzer Space Telescope, each one looking at a different wavelength regime and each one taking advantage of being above the atmosphere, which is why we put telescopes in space. And as discoveries piled up, it became clear that one needed to have an infrared telescope that could see finer detail, could see detail at the level of the Hubble Space Telescope, but at the longer wavelengths. And so that led to the development of the James Webb Space Telescope.
Infrared astronomy is basically centered on wavelengths that are longer than visible light. It's basically heat rays. And so trying to observe them from the ground is actually a losing proposition. We try it all the time, but the telescope's warm, so you have to fight against all the energy that's being poured out by the telescope. So the Webb telescope goes in space so it can be cooled. So it's going to be a cold infrared telescope without those big backgrounds that we have on the ground. And it's going to allow us to see very fine details because its mirror is so big. So that's why it's so exciting.
As discovered back in the 1920s, the universe is expanding. We've known for a long time that there's something called the Doppler shift, so that if something's moving away from you, the wavelengths get stretched out. If it's moving towards you, they get compressed. Stretched out means they're getting longer and redder. Compressed means bluer. So if we want to look at the most distant galaxies, which would be the first ones to form after the Big Bang, we have to account for this expansion, shifting all the wavelengths, and you get to the point where the only wavelengths that are left are ones you can observe in the infrared. So I came to the University of Arizona as a postdoc, actually hired by George. And I came here because I knew that this was where things were happening and where infrared was really going to grow.
University of Arizona is actually where infrared astronomy got started. Basically, it was founded over in the Lunar and Planetary Lab. And ever since then, the University of Arizona has led the way in infrared astronomy. We've been very involved in the very first infrared space telescope, and now, of course, we're central in providing the instrument for the James Webb Telescope.
Body health and emotional health.
George, you hired her.
Part of it is that any field of science is very intense, and you have to be very focused on what you're doing if you're going to be at the state of the art in the field of science. And so you can't really talk to anyone other than another astronomer because nobody else will understand.
Well, he hired me, and we had to spend a lot of time together. And over time, it became clear that we were not just interested in the professional work, but that we had other interests in common, and one thing led to another, and eventually we got married. Even
So working so closely together has the advantage that it's almost like a single brain thinking about how to do something. And it was possible to kind of intuitively understand what would be a better design and a worse design.
My role on the JWST project is as the principal investigator for the near-infrared camera, NIRCam. NIRCam was envisioned as part of the original instrument suite for the Webb telescope. And so when NASA put out what's called an announcement of opportunity to propose, George started thinking about, well, we shouldn't put all our eggs in one basket. Maybe we ought to propose for a piece of the mid-infrared instrument action. And never did we think that we would both get selected. But of course, that was history.
My instrument is the mid-infrared instrument, commonly called MIRI. And it's the instrument that lets us look inside interstellar clouds of dust where the very first stars are forming or just starting to warm up.
Well, NIRCam and MIRI complement each other because they work at two different wavelength ranges. And so if you want to do some imaging, you would need to use both instruments together. We got selected to work on the instruments in 2002. And it wasn't until about 2007, 2008 that the designs were all agreed to and people actually started building stuff. And what's going on now in August of 2021 is doing the final bits of assembly and getting ready to pack it up to ship to Kourou, which is where the telescope will be attached to the rocket.
After launch, the next big item of suspense is unfolding the solar panels, and they're batteries that last for a limited amount of time to power getting them out. The telescope is so big that there was no rocket fairing that could fit inside, so everything has to be folded up. And so there are many, many different parts that have to be articulated and extended and stretched and so on. There will be an extended period of tension because any one of those things not working would be a very big problem. And she's got to line it all up.
Right, about 35 days after launch, NIRCam will get turned on. Each of the 18 segments of the primary mirror will make an image of whatever star we're pointing towards. And then as the telescope finishes getting cold, the other instruments will get turned on. And then we'll move into what's called regular science operations, where we'll start taking data, and there'll be big excitement when you see that your instrument works, and then there'll be big excitement when you finally start getting the data for your project. So you promise this wine's going to be really good?
Yeah.
Okay. What did you promise?
So what are we going to do when we get our data?
See what it means and write papers.
You're going to find the first galaxies, right?
I hope so.
I think the biggest discovery that Webb's going to make is something I can't tell you. And the reason is the big discoveries are always things you don't anticipate. So it's very, very likely with this big breakthrough in what we can see and how much detail we can see and how far away we can see, that astronomers, not me, but somebody will find something just totally mind-boggling. And that's pretty much the history of astronomy. To get into space, you have to pay a big price in terms of your career and basically your whole life. The rewards are worth it, but it is a big price. So commit yourself completely to doing what you're doing, and that allows you to do it at your very best. And if you're in a marriage with somebody else that's completely committed, then there's a resonance that lets the two of you have a really big impact.
Sign up for the long haul, because you never know how much more time it's going to take. And that's a variant of being committed, but it's the same basic idea.